Hey guys, welcome back. Well, I was out night before last with this new telescope. This is the William Optics Gran Turismo GT81 Model 4, so it's just been released relatively recently by William Optics. The key feature that's new about this version of the GT81 is a camera rotator, which is very useful. There may be some other changes as well that aren't as obvious, but anyway, this is a nominally a 478 millimeter focal length telescope. It's a 3-element design, and I have a focal reducer, the recommended focal reducer, the FLAT6Aiii Model 3 back here. We'll get to that in a minute, but let's just go through an overview of the imaging train. And of course, the feature that is very much appreciated with the William Optics telescopes is the dust cap that has the integral Bahtinov mask in acrylic, so that's a very nice feature. Now, with the tube rings installed, it's a very short length tube, and the handle attached to them which sets the spacing. The dew shield is, by definition, it's extended. Now, they do give you a set screw to hold it in place, but that's not necessary with the tube rings installed because it's not going anywhere. The lens elements are about right in here on this telescope. You've got a focuser that has about a travel of 70 millimeters. Right now, focused as it is at the infinity, so to speak, it's about a 27 millimeter extension, so it's very comfortably within the range of travel of the focuser, so that's nice. They do tell you what the back focus is with the focal reducer installed, and that's about 62 millimeters back from this face back to the sensor. Now, the nice thing about this focal reducer is that it's adjustable, which means that I have 55 millimeters back from this face back to the sensor, which means I need to set the extension, and there's a graduated scale on this that's covered up by this Velcro strap, but there's a graduated scale on here that will show you what the extension is, and right now it's set at about 7-ish millimeters. We'll come back to that as I talk about the method I used to set it. But continuing on with the imaging train, I bought another FocusCube 2 to install here. So as you can see, I have the scope mounted on a Celestron plate, that dovetail plate that mounts well or interfaces well with my Celestron CGEM mount. And then I have another FocusCube 2. I have one of these installed with my Explore Scientific ED102. I like it a lot, so that's why I bought another one. It has an L-shaped bracket that comes down, and then it attaches to the base of the Celestron tube. Now, one of the things is very tight fit. This dovetail bar that comes with the GT81 cannot be moved forward because there is no corresponding hole. You probably can't see it here, but there's no corresponding hole at the back end that mates up with a hole in here that has the right spacing set by this handle. So this is as far forward as I can move that dovetail plate, and it does interfere. At least it has the potential of interfering with the L bracket of the FocusCube 2. Right now, it is pressed up against the dovetail plate, and it is screwed into the Celestron plate. And I was able, with a little bit of free play I have with the tube, to slide the tube back ever so slightly just to align the focuser shaft with the shaft of the FocusCube 2, so that all works out fine. I've used the focuser now, both initially focusing on a distant object about 800 feet away, and then a couple of nights ago out actually in the nighttime sky focusing. I've got a dew strap here mounted around the dew shield, and it plugs into the port here on the Ultimate Power Box 2. The Ultimate Power Box is mounted on a plate. It's a perforated aluminum plate that you can buy to tell them the size and the hole size that you want, and you'll get this perforated plate. I have it, I painted it red because I have some red paint, and then attached it to the handle using a single screw here. The screw is easily accessible, so it's something I will check for tightness each night before I go out. The power box is attached to the plate with Velcro, although you can see here I've got these lovely rubber bands here just because a little more connectivity is a good thing, I think. But it's mounted forward here so that I can slide a little bit the telescope back and achieve a little better balance of geometry here. I've also got it biased off to the side over here to try to compensate for some of the weight of the FocusCube 2 over here. You can see there's a lot of cables, but it's a fairly compact layout considering the number of cables that actually have to come down from the scope. For example, these two cables here are the DC cable for the that power the cooler on the ASI 1600 camera, and the other is DC cable, comes back and powers the focuser. Then you've got this white USB 2 cable that comes to the focuser. The focuser also has a temperature sensor, its own temperature sensor, which plugs in here and wraps around, and this is the temperature sensor for the FocusCube 2. And then we have a USB 2 cable that comes down. This is the communication with the mount, data communication with the mount. I've got another USB 2 cable that spans over here to the guide camera. There is the USB 3 data cable that comes down and goes back into the ASI 1600. And then finally there's a power cable, and this is kind of new for me. What I had been doing is wanting to power the mount through the USB 2, and I had mounted or had connected the power cable through this DC 12 connector, 12-volt connector here, which allows me to turn on and off that power to that particular port, as you can with all of these ports here, with the interface for the power box. But for whatever reason, it never would work. I could never power the mount, even though, according to specs, there's more than adequate amperage coming out of this connector here down for what the mount requires. And so for some reason it never would work. However, when I move that cable back to the always on 12-volt source here, I think it might be rated at 1 amp higher, if I'm not mistaken. And I've been using and powering the mount off of this cable here that comes down from this port, and it's been working fine for the past, I don't know, 4 or 5 nights of imaging. So I'll keep my fingers crossed, and hopefully that eliminates having to use that AC DC adapter that I've been using to power the mount. So I've got these 2 cables coming down to the mount, so they don't move much when the mount slews and RA. They don't move at all in deck. They just have to accommodate a little bit of radial motion extension of these cables, but other than that, it's not bad at all. And then the other 2 cables that come up from the ground are the primary data cable that comes in here, and the power cable that comes in here, and those need to have enough slack to accommodate RA and deck motion. But other than that, this is a fairly compact arrangement, and when I'm done using this telescope, I simply have to detach it from this screw here, take all the cables, and just attach it, for example, onto the handle of the ED102 or the excess real estate that I have on the Celestron plate for the Red Cat 51. So I should be able to plug and play this little Power Box 2 whatever scope I happen to be using. For my imaging, it's the same imaging train that I use for all of my scopes. It's just that imaging system moves from one scope to the next. For the ED102, GT81, and Red Cat 51, I use the ZWO off-axis guider with an ZWO ASI 290 mini camera here. And then I have a 10 millimeter spacer between the off-axis guider and the ZWO filter wheel, and then I have my ASI 1600 camera. Now, one of the key things I wanted to do the other night, the first use of this telescope, is not so much imaging, but in setting the back focus for this adjustable field flattener focal reducer element here. And it's a bit without the rotator, this would be quite a bit of a complicated task, but with the rotator, it makes it quite easy. The nice thing about having this field flattener is that it's a fully threaded connection all the way back to the scope. There are no compression rings or set screws. You just have, you can adjust the field of view, or the orientation of the field of view of the camera using the camera rotator, which is nice because you do need to make adjustments like that even for this wide field scope. For example, in shooting the California Nebula or M31, I'm going to need to rotate the camera, probably in the configuration it is right now, as a matter of fact, to be able to get those longer objects diagonally across the field of view. Let's go over to PixInsight and take a look at the results from that first night's out imaging. We have in PixInsight the image I took outside with the first image I took with the field flattener set at its nominal spacing for my particular camera. I've got a back focus from the forward face of the off-axis guider back to the camera sensor of about 55 millimeters. The flat filter and focal reducer requires a 62 millimeter back focus. So I knew that I needed about a 7mm extension in here in order to achieve essentially optimal flat field effect. Now, so this element here between the back face of the rotator on the focuser and the forward face of off-axis guider is the William Optics FLAT6Aiii version 3. Now, in doing these tests, the thing I did was to loosen up this locking ring here and then take a hold of the camera as I rotated the back end of the field flattener using the rotator element on the telescope. The last thing you want to do is rotate the back end of this because all these cables get twisted around. A counterclockwise motion of the rotator translates into a relative clockwise motion or rotation of this end of the field flattener, which means that you would be shortening the effective length of the field flattener. So that's the first thing I did. So this is the nominal setting that I use for the field flattener based on the assumed measurement of my optical train, and setting the initial extension of the adjustable field flattener to about 7mm. This is the result I got. Of course, we can't see anything from this, so we need to zoom in a pretty good bit and then go to the corner. There is a star cluster here in the center of the image, but we're not interested in the center of the image. We're interested down in the corners. And as you can see, down in the lower left-hand corner, I have a little bit of a stretched star effect. Going up into the upper left-hand corner, I've got some stretched stars here. Going in the upper right-hand corner, we're in the kind of the shadow zone of the off-axis guider, so that's not very useful. And then down here, we have some pretty good star shapes down in the lower right-hand corner. But obviously, we have some defect down here in the lower left-hand corner. So I wanted to make an adjustment to see if I could get rid of that and reclaim more or less circular stars down in the corner. So the first thing I did was rotate the rotator end by one full rotation in the counterclockwise direction, which meant that I was shortening the length of the adjustable field flattener. Now let's zoom in on that one and take a look at the same corner down in the lower left-hand corner. And now things appear to be quite a bit worse. If we look at the same location here, it looks like I've made things worse. The stars aren't going to be quite the same because even though I'm trying to hold the camera still from rotating, it does rotate a little bit. It doesn't take much rotation to change the star field a little bit. But by and large, you can see the effect. We have what looks to be more stretched stars in the lower left-hand corner. If we go up to the upper left-hand corner and compare what we had here, I had stretched stars here. It's maybe not as bad in this case. There is going to be some tilt that I can't get rid of by simply extending or contracting the adjustable field flattener. But that's just the way it goes. And let's go down into the lower right-hand corner. And here there might be a bit of stretch going on in the other direction. It's difficult to tell from this picture here. I would say the picture here on the left looks a little bit better than what I'm seeing over here. So the thing I took from this is that the 1 times counterclockwise rotation was the wrong way to turn this, and we needed to turn the flattener the other way so that I had a net 1 turn clockwise relative to my nominal position. And so let's look at those results, and we'll go down into the lower left-hand corner. And I think we're a little bit better. It looks like things improved a little bit compared to the initial offering. This is what we had. This is what we have now. Seems to be maybe a little bit better. And in the upper left-hand corner, quite a bit better here, I think, for sure. We have pretty much round stars. Let's go in the lower right-hand corner and see what we have. Fairly circular stars down there, and in my original nominal position, not too bad here either. I decided that I would go a little bit more and see what I would come up with, so I went 1.5 clockwise rotations, and we have this result in the lower left-hand corner. I think the stars here are fairly round in this corner, so that's pretty good. Let's go over to the lower right hand corner and compare to the lower right hand corner of my starting position. And I'm probably getting a bit more stretch over here than I did over here. This is the 1.5 rotation on the left and the 1 times rotation on the right. Let's go over to the right hand side. I would say, if anything, I'm seeing a bit of stretch going this way, essentially tangential to the circular field, so to speak. And here I'm seeing a bit more of a rotation or a stretching along the radial axis. So it seemed like we're something between 1.5 to 1 times rotation. And if I go over to the left hand side, I have pretty good star shape over here with the 1.5 rotation and a bit stretched stars in the 1 times rotation. So I made a final adjustment where I backed off from here back to about a 1.25 rotation, which should give me stars in between what I'm seeing here and what I'm seeing here in the lower left hand corner, and stars shapes something between here and here in the lower right hand corner. So that should give me a reasonable balance between stretched stars in the various corners. So this is perfectly reasonable, and I thought it was fairly easy to make these adjustments. Another thing that I did in doing this this initial characterization study that first night out with the telescope is to also characterize the focuser. The thing I've done before, and I have a video on this, so I'm not going to beat the details of this together, but I like to use the Bahtinov mask. And what I do is set the focuser to a position that's outside of focus on the outside, on the long side, and then take a picture with the Bahtinov mask applied. And here you can see an image with the Bahtinov grabber. I used a Bahtinov grabber because it allows me to define a large area to capture the diffraction spikes. APT's window doesn't really permit that good of a capture area. It doesn't allow me to adjust the capture area. So I use the original Bahtinov grabber just to capture a screen area. I have the focal length adjusted to 0.385 millimeters and the diameter at 0.081 millimeters of the aperture. And of course the pixel size is 3.8 microns for the ASI 1600. And then what I'm doing for a given focuser position, I'm just taking a picture and having the Bahtinov grabber identify the spikes and then tell me over here what the focus error is. In this case, it's 2.93 pixels. It measures error in pixels. And so in this plot here, what you're seeing is I start from an outside focuser position. I measure the focus error using the Bahtinov mask and plot that point along this axis, and then move in by a certain amount, get another take another exposure and get the focus error associated with that, and just repeat that process all the way through a focus error of 0 pixels, which is perfect focus ideally, and come on out to the other side. And then once I get to the end, after moving the focuser in, I step way out and then way back so that I eliminate any backlash that might be present, and I just start recording those same numbers coming back through focus, but now I'm moving the focuser outward in the outward direction. And you'll notice where the inward direction and the outward direction cross the 0 error line, that difference in focuser positions is actually the backlash. And so in this case, the backlash for this particular focuser combination of the GT81 OTA focuser and the Pegasus Astro FocusCube 2 is about 70 steps, which is fairly, it's about the same as I got with my Explore Scientific focuser and that FocusCube 2 that's on that particular telescope. But here I got 70 steps for backlash. And the slope is also extremely important because it tells us, if you take the inverse of the slope, it's 25 steps per error of pixels. All right, so it's 25 steps per pixel error. Now, the Bahtinov mask, or the critical focus zone, is about plus and minus 1 pixels, say. So that means a fine focus step of about 1/4 of this number, or 1/2 of this number, is about what you want. In other words, if you were just out of focus right here, moving the focuser inward, by about 12 steps would put you at about halfway into this green area above the line. Another 12 steps puts you on the line. Another 12 steps puts you just below the line. And another 12 steps will put you just on the outside of being in critical focus. So for me, I'm defining the fine step or fine adjustment focuser step as about 10 to 12. If you're using this in combination with a V-curve or hyperbolic curve fit type autofocusing routine, you could probably use about 4 to 5 times these numbers to make a single step for the autofocus routine. So I might use 40 to 50 steps for each big step of for the autofocus routine. So anyway, this first night out with the new telescope was successful. You don't plan on getting much done in terms of imaging, but what you are trying to do is characterize the system so that the next time you go out, you have all of the performance characteristics identified. We were able to set the extension length of the adjustable field flattener to the right length to minimize the amount of stretch stars in the corners. We were also able to characterize the focuser and found that our backlash is about 70 steps and that our fine focuser step size is around 10 to 12 steps in length. And I'm ready to go out and get some more imaging done. So hopefully bring on the clear skies, and I'll talk to you guys later. Next time I'll show up with some images. See ya.